So hi, my name is Ólafur Waage. Have fun promote. Wow, words. Let's get the stress out. Hi, my name is Ólafur Waage. Have fun with that name. This is playing video games one frame at a time. This is my face. This is my name. This is my title apparently, and this is where I work. And if you type this on Google, you will find me. I'm all over the place. I will yell at the internet everywhere, and you can yell at me. There's places on the internet where you can yell at me. That's really cool. I work at this company called Factlines. I talked to marketing yesterday, like, can you give me a marketing slide, a thing I can show? And they're very boring, very like technical and very accurate, which I thought like for programmers, that would be cool. But basically, if you work at a Norwegian company and you know these words, and these words scare you, call us. I think that's the best way to do it. Because some of you might recognize these words, and if they do and they scare you, that's the one to call. All right? Cool. So, I've had a theme in the past couple of years of my talks. And I always start with a philosophy quote. Gotta have a good philosophy quote. So people say that nothing is impossible, but I do nothing every day, which is, of course, the philosopher Winnie the Pooh. Yes. All right. So who am I, maybe? For those who don't know who I am. This is me when I was younger. Well, like Mitch Hedberg said, all photos are of me when I was younger. But I worked on air traffic control systems for a couple of years. That's a very interesting field to be in. I was in the gaming industry for 7 years. That's also a very interesting field to be in, but for a very different reason. I'm in that photo. If you can spot me, you can raise your hand. And then I was, there we go, a consultant in Norway for a couple of years as well, which is why I'm here. So this is me yelling at you, and then you can yell at me. Good. So, what is this talk about? All right. A good way to describe this talk is, it's a bit of silly fun, a little bit. It's a bit of curiosity. Like you've had these projects where you're like, I wanna go down the rabbit hole. I'm gonna go all the way and see what happens, right? And there are, when I went down the rabbit hole, yes, I did find some real life use cases, and yes, there will be a slide at the end that will show you those use cases, but it's mostly part 1 and 2, all right? And I asked you in the beginning, are you ready from Sicilians? Everybody raised their hand, so that's good. This is also probably not an area a lot of people have thought about. Because I can see maybe not everybody here, like who's here is a gamer, like a gamer? Yeah, it's like half the room. So this will be very interesting for your other half of the room. Good. Also, this is a caveat for people who have been to my talks. I did a talk here last year that was way more serious than this one. It was like about education and learning and how our brain gives information, takes information and all that. About how humans learn information. And in that talk, I said, and you can have like a cut with like, unfortunately, like an old-timey video. Unfortunately, in this case, there is considerable evidence in many situations that this strategy, the 1-hour lecture, is rather poor. Lectures may inspire, this is from 71, by the way. Lectures may inspire, motivate, and inform, but it rarely fulfills the principles of effective learning, right? It is certainly inadequate for developing high-level skills. 71, and it's been shown in other papers and tests after that. So I cannot, in good conscience, make a talk the year after where I'm trying to teach you something. Because that's kind of weird, right? Yeah. So instead, I decided to make a fun talk, right? So about some real-life applications they might not talk about. And also, again, there's a lot of caveats here. I will do stuff to video games in this talk. Yes. If you are going to do similar stuff to video games, I would like to ask you nicely, only do this to single-player, non-online games, right? I'm giving you the tools. Please be nice. Please don't do crazy stuff. Like I'm not the police, but be nice, right? You want people to be nice to you, so you should be nice to them. Cool. So, boring backstory. Playing video games is great fun, but I'm also a programmer, right? I think so. Someone told me that. How can I marry these two things together? And some of you might think, like, well, you can make games. Well, I worked in the gaming industry for 7 years, so like, okay, cool. Then what, right? I'm done with that. Even though I didn't make any games, I just worked on games. But what if there's another way, right? There must be another way. Games are just applications. So can we do something to control these applications remotely? Can we have some fun with the games remotely? What are the different challenges you will, like if you have this idea, you say, I'm going to control games remotely, right? You will have a couple of challenges, and I will show you, like basically like, you're going to hit your head, and I will show you where, right? So, and can some of this apply to interacting with other software? Because yes, it can. Cool? Okay, so now, caveats done. That took half an hour. No. All right, level 1. Since we're in a video game, I have to have levels, right? Level 1. What if the game that you would like to play remotely or programmatically just supports it, right? That's level 1. That's the easiest level. They support you playing with it programmatically, so let's play that game. And that game is, yeah, half the room is going, yeah, the other half is, what is this? So this is Doom, right? Doom is a 1993 first-person shooter. You shoot the demons in the face, everybody's happy, right? And the thing is, it's 93. Games in 93 were kind of weird. For those who were playing games in 93, games in 93 were kind of, I don't know, they're not this. This was a thing. This was revolutionary. So they changed how you think of a first-person game. I'm in the first person, I'm interacting with the world. So that's kind of, other games kind of did that, but this was there was a point in time where this application was installed on more computers than Windows, right? This application crashed university networking systems based on how many people wanted to download it. Like this was the thing. They also changed online multiplayer because not only is this a game that revolutionized how these games work, they also had online in 93, which is like, what? Okay. And game modifications, because they gave the specs to how everything worked in the game. So not only did they like, hey, here's a revolutionary game, also here's how it works. And people are still messing with this to this day. Like there's a big YouTube series this year about a person that played with this, made a horror game that was very strange. If you Google My House on YouTube, you will get that one. And also, this last chapter, video game speedrunning, which is a concept probably even fewer of you know what is. So, I can't go over everything, but I'm actually looking at the last one, video game speedrunning. All right, so this is a human thing. Whenever there's a timer, people want to be the best or the fastest, right? Because with the timer, it's my number, it's your number. All right, I won. It's as simple as that, right? Doom is no exception, and I love this screenshot because this means that someone went through the whole level, did not kill any monsters, but found all the items and found all the secrets, and did it in 1 minute, which is like, okay, but it's a fun screenshot. And at the bottom you say, the game did it by default. When you finish the level, it didn't say, congratulations, here's the next level. It said, you did this good, which is like, no game did that. That's another thing that was just weird. Okay, so Doom is no exception, because at the end of the stage, there was a timer. Cool. And then, of course, internet is blowing up. So what people did was, well, how can I compare me with you, right? So this is a version of the game called Ultimate Doom. These are the first 9 levels. And this is how fast people have been playing that game. So level 1, Hangar, in 8 seconds. That record was made in 2019. People are still playing. People are still trying to beat this. People are still trying to be the best. So again, whenever there's a timer, my number, your number, it's very simple. Cool. And you see a file over there. Okay, some of these are from like 99. So like, is this a video? what's going on here? Like, what is this file? What happens when I click on it? Well, if you download these files, you'll notice they're tiny. 7 kilobytes, 5 kilobytes. What? What's that? Even one is 1 kilobyte. So they're pretty small. The reason is that these files contain the input that the user pressed when they were playing the level. Nothing else. I pressed the forward button and this time. I pressed the mouse button here. I clicked the shooting button, whatever. That's the only thing this contains. So what you're then playing, when you play these files, these are called demo files, because they're demonstrating something, you'll get all the inputs. So here's the header, if you want. This is the header of the file, showing you the game version and the level and what kind of version of the game it is, and some flags you might set that might change how the game works, right? And then after the header, there's just a line, bunch of lines. Now these lines are saying, did they press forward? Are they pressing forwards or backwards? Are they pressing left or right? Are they turning? How much? What's the angle? And then the actions. Did they shoot the gun? Did they open the door? That's it. And then you have the next line and next line, right? So there's software called XDRE, and these are the lines. This is what you're playing. And there you can have the game on the side, you can have the files, you can see all the states of the game, and then when you go forwards a few frames, the character has moved forward a few frames, because they pressed move forward, and they're facing in the direction 25, which is the angle they're facing. And then I turn a bit, so facing a different angle, etc. I move further into the level. And that's what's saved in the file. So when you're playing back that demo, you're just playing back that file. Cool, right? That's kind of neat. But how does that work? How can you make sure that this always works? Because this always works. This always works. Again, like you had the version of the game, so there's like probably different caveats to that. So this is possible because of one thing. And here's actually for those who don't know, they released the source code to the game, so you can go and read it. And yeah, it's very 90C. So if you want to read 90C, you can enjoy that. Doom is deterministic. Okay. Doom is a single-threaded application where every entity in the world map that you're playing in patiently waits their turn until the game says, now do your thing. Okay, I move one step, and then they wait their turn. And always in the same order. But you might think, what about random stuff? And here's like some more code. If you're interested in looking at old code, that's always fun. So, but when they want to do something random, well, there is no random number generator, but there's a table with like randomest numbers. There's 256 of them. And when any of those entities, they could always be doing things in the same order, they're very patiently waiting in line, and they say, I'm going to do something random. I might wake up, or I might do a different animation or whatever. They say, give me a random number, then they happen to get one of the numbers in that list, and then that index on the bottom is incremented. Just an index. And then the next thing that wanted to do something random, they'll do the next thing, right? So that's how random works in the game. So it's not really random, but it's a game. So it feels random. And that's the only thing that actually matters. It feels like, hey, this is weird and random. So that index is incremented, and then the next entity will get the next number. That could be you. It could be like when you're shooting the gun, the muzzle flash looks slightly different, or how much of damage you do with your gun. If you shoot now, you do 10 damage. If you shoot later, you do 20 damage. That's because you just got a different number. Oh, and people have messed with this, where they change the game to all the numbers to be 0, so everybody behaves the same way all the time. It's very strange to watch. So, okay, that's neat, right? But what if you wanted to take Doom and convert it to C++? So this is something that Jason Turner started doing in a video a couple of years ago. And then Patricia Oz took over, was playing with a bit more. It's like a neat thing. Like, can we, because it's written in C, can we make it more C++-y, right? And this is kind of one of those like forever projects that's probably never going to be finished. But the question is, I want to convert it. That means I'm going to do changes to the code base. So how can I move forward with that project knowing that my code changes and my refactorings haven't broken anything, right? So you can play the game or you can write unit tests. That'd be cool, right? But we have the tool in our hands right now. So approval testing is a thing. It's a methodology where you focus on comparing the output of the old known bit of code with the output of your new code. So the physical output, okay? So it's more like a git diff. The game or application is going to spit out some output data, and then you do some changes, and you check out the new output data, and then you do a git diff. That's the basic idea. And this is used in legacy software where you have no access to anything, okay? So this is useful when you do want to do a complete rewrite when the original source might not be available or obfuscated or some problems with it. So this is a great tool. Approval testing. So Doom can run the old demo file, and when you're done running that demo file, you get a nice little screen that says, we played this map for this long, we killed this many monsters, found this many things, right? This is output. Cool. Yeah, the thing I said. So what if I play this demo on the new version? I did some changes. I played the demo again. Do I get the same numbers? Like, because if I change something about the movement of the guy, and then the guy walks into a wall, then he's not be able to finish the level, or it's going to take longer, or he's not going to kill as many enemies. So there's a diff, right? I have old diff, I have new diff, a new file diff, right? So, and another tidbit, the game doesn't need to render on the screen for the simulation to run. Graphics are just a nice representation of whatever's happening, the actual state of the game. So we can add some flags where we can run the game in the terminal. So the game runs, and there's no graphics, and I not get the output. So I can run this in like a Linux box that has no screen attached to it. I can do that. That also means that I don't need to run the game at 30 FPS or 60 FPS. Like it's a game from '93. I can run it as fast as I can. Just go through, it's deterministic, it's always going to do the same thing. So I'm just going to blast through all the operations, no sleep, no nothing. We have an output. Cool. Okay, so the simulation is the same. So are we putting one and one together? We can play the game using a good known version, collect the bunch of output statistics that says this is the good known version output. We can save those demo files with the text output that we did. You don't have to read this, but this is basically a diff. I'm running a command line diff. So I run the game with no graphics, no sound, no mouse. I want the stat output, and I'm running the demo. So I run this on all these demos, and what I can then do is I can run Doom in GitHub Actions. On all these different computers, all these different operating systems, and 64-bit, 32-bit. Because so I know now. I did some changes, I run it in CI/CD, run it in GitHub Actions, and here, it took 10 minutes to build, and if you can read the fourth to the bottom, it's called demo check. It took 0 seconds. And I'm testing like 30 different demos. Some of them are 6 minutes long, because I just run it as fast as I can. It's deterministic. I always get the same output. And then, yeah, here's some output. Here's for those who played the game, this Doom shareware thing at the beginning. So we have the shareware WAD in the GitHub because you can't share it. And all those demos are from the shareware, so we don't have the actual full version of the game, but we have the demo version of the game to run the demos. Yeah. But then, yeah, here we go, all green. And then I can go and do my next refactoring and change. Cool? Cool. I'm on time. I'm good. Level 2. All right, time to level up? Good. Remember, I have 300 slides. Let's go. So what if the game you want to play doesn't have the support that Doom does, right? You can't just programmatically mess with it like this. Cool. Bejeweled. Who's played Bejeweled? 1/3. You should play it. It's very fun. So Bejeweled is a match 3 game. You have these gems on the screen. You pick a gem, you move it left, right, or up or down, pick a direction. And you want to create a 3 of a kind or a 4 of a kind or anything more than that. Cool? You can also, join 4 more gems for bonus points and all sorts of fun, and things will explode. It's very colorful. So, after a match has been made, those gems disappear and the board falls down and new gems arrive. That's kind of how that plays. So, we want to play Bejeweled 3 automatically. We want to write some software that plays Bejeweled 3 for us. Like we wrote some software that played Doom for us. No, we want to do this now. This is our next project. So, step 1, what gem is where? We need to recreate the board. We need to know the state. Plan 2, pick a good move. Do something good once we know where everything is. 3, move that gem. Move it to a new location, that kind of stuff, and repeat. And then we can play the game. All right. So, project is a C++, CMake, VC package project. Looks kind of like this, with patterns and mouse. And we have OpenCV. So for OpenCV, we are taking a screenshot of the game, saving that image texture, and then we are doing image manipulation. Because the game is a separate process, we can't touch the game process, but we can observe the game process. We can look at the game, and in this case, we're actually just looking at the pixels. So we're going to look at the pixels of the game. Yeah, and for those who don't know OpenCV, it's a pretty old, real-time computer vision software. It has a lot of support and libraries and all sorts of extra features. Very cool. So, step 1. We will spend a little time on step 1. What gem is where? Oh, and by the way, if you're in a big screen and you run the game, it's actually this small. But I will make it bigger for you. So, when you play in this size, the game board is 64 by 64 pixels. Well, each gem, sorry. It's a very nice round number, right? That means that the start of the board, the 0 position, is at 261.37. Cool. This is also known. The game board is shrinking and shrinking and getting bigger. From that information, I know where each cell is. So I know that the white gem is there. That's the coordinates of that. And the red one is then 64 pixels in, and the green one is 64 pixels down from that. So I know that. I just don't know what gems they are yet. Okay? But how do I know that this is the green gem, right? Okay. So I started off simple. Let's just look at the center pixel. And if it's greenish, because I know where everything is, so let's look at the center one. It's like, look at the RGB colors and this looks greenish. Let's try that. But there's a problem by doing that. And I tried that. I implemented it. It kind of works, but there's a problem. If you click on it, it spins. So that doesn't work. Okay? But generally, if you avoid clicking, which in a game about clicking, yeah. But if you avoid clicking, yeah, that works. Cool. So, I have this library, OpenCV. I initially just used it because I wanted the image capture of the game. So let's use it. So they have a bunch of stuff. So I thought hey, let's be cool. Let's use some what's called template matching in ImageTV. Because you can look for patterns in images and do image recognition and that kind of stuff. So here's face of Messi. He's kicking some ball or something. Cool. So here's he kicking the ball. And if you can see, you can use the mouse, the bright spot here, that's the closest match to what you gave me as a template. Others have a match because it's like the statistical analysis, so things kind of match. But that point in the center, that's the best match, right? And you have different kind of algorithms or different matching methodologies you can use. And so the face of Messi is over there in the photo, right? So I give it this little snippet, it says me, yes, it's there. And I'm thinking, perfect, this is great. So I created these nice sample images of the gems, right? And I'm using them as the templates. And here I have the game, and then I have an application on the side that is the matching or will show me where the matches are. And here they are, the little green circles, the green outlines of the matches. So do you see the problem? Hands up for the problem. Yes. The red one over there. Yes. And I have this, the algorithm has a threshold of how aggressive do you want to be with this matching. And I had it at 55 of some number, and it didn't match this one. So I'm thinking, let's change it. Let's lower the threshold. No. Then after playing a little bit, then it matched this orange one, which was kind of glowing because it had like some effect on it or something. That doesn't work, okay? But why? As a programmer, you're like, why doesn't this work? Cool. So let's use OpenCV to our advantage. No, I did that. So because what they do is they make it black and white. That's what they do. So that means a lot of the gems are kind of similar-ish or same-ish. I lost the color info, which is the important bit. So let's go back to color. Because I looked, like the orange is there. That's kind of pretty obvious of where it is. There's a thing called HSV, hue saturation value. So I'm turning the color stuff into a kind of linear algebra problem. Where is on the wheel is the arrow pointing, right? So I grab a 32 by 32 center area of the gem. I ask OpenCV, what's the average color of that center gem? I check that color against HSV. And if you're in that kind of range, like if you're pointing roughly there, then you're green. If you're pointing roughly there, then you're red or something like that. And it's over there. So I went through and played the game, and I took the average values of every single, this took like 2 hours to go through and get all the center pixels and get the color information. And I made a chart. What's the highest hue value? What's the lowest hue value? And a lot of them are completely separate. That means that you have a hue value of 100 to 110, you're blue. If you're 60 to 80, you're green. But you can see that for purple and red, which is the one I haven't highlighted, there's a little bit of overlap. And the orange and yellow are kind of too close, right? A little bit too close. So write a function. You have the HSV value when you want to detect. You can also send in the red, green, blue to do disambiguation. So say like, they are kind of close, but then if there's a little bit more in the blue range, then it is the blue one, if I'm unsure. So the functions, I extract the values, and I just ask, if the hue is above 85 and less than 115, you're blue. If you're this value, you're green. If you're this value, you're purple, etc. It's a very boring function, but it works. That absolutely works. So we have this. Beautiful. Now I know what everything is, and I can click on the gems, and they can spin and do all the funky shit. There's one, there's one edge case, but I'm ignoring that for now. Because step 2, let's pick a good move. So what is a good move? Again, initially, let's do some cool deep learning algorithmic but I just come off the color thing. So let's do something simple. Let's try the simple solution first. So it was actually a pretty good solution. So the simple solution was, let's just play the game a little bit and see like how the game acts and reacts and whatever. So I played the game a little bit. It's not, I played it before, so it's not, it's more of just a funny screenshot. And I had an idea. An idea was, there aren't actually that many moves in the game. The number of situations you have aren't that many. Because now we're ignoring the color. We just need to find matches. So can't we just list them, map them out? And you can. So I made a system where you have, you want to have A, B, C, but there's something in the way. The X is in the way. So you want to get the C from the X and over the X and over to the B. So you're moving the gem. So it looks kind of like this. And I want to move the orange over the yellow, and I have the match, right? So this is the situation I want to look for, because I can do a move and something cool will happen, right? So I have a pattern where I have a points. So I have the A point and the B point. So it's the 0 and the -1, because the A point is a center point. So going backwards in the X direction. And then I have the C point, which is then -3. I can call it something, and then I have a solution. What do I need to do to the C point to get it over? So I need to do +1 on the X-axis and nothing on the Y-axis. Then it will be -2. They'll all be together, and we'll be happy. I can give it an ID, and I can give it a value. And I put that in the list. And here's a more complicated one. So we have like this corner piece, and I want to move the red one in. So I have all the points, and then the last one is in the pushback is the one I want to operate on. What is the operation I need to do? It's the solution direction. And you see that I have a value of 3, because this is a better move. I get more points for this than the other one. Cool. And then I found out that there's 32 moves, which is, again, a really nice round number. Really cool. So, good. But there are multiple moves on the board. Which one should I pick? Because this one is 4, and it's a higher value than the others. But what if all of them are the same value? Which one of them do you pick? And what I found is you pick the one lower on the board. Because when that matches, everything moves down, and there's more opportunities for other gems to, by happenstance, match. They just happen to match. Because if you pick the one at the top, only like 3 or 4 of them move down. If you pick the one on the bottom, like 6, 7 of them drop down. So there's more matching. That's the one I say, if it's ambiguation, sort them by y-axis, pick the lowest one when we move on, right? Cool. That was step 2. Step 3, which is the simplest of them all, move that gem. Okay. The Windows SDK has very nice mouse inputs. So let's use them. And I basically want a function like this. I have the window. I know where to start, because from all the stuff before, I know where everything is on the board, and I know where to go, because from the solution things, I know which X and Y direction I want to go. So this is my function. So first, what I need is, because I know where everything is in the game board, I don't know where it is on your desktop screen. Right? So I need to translate that from use system metrics to get the window and get the scaling of the screen. And then I need to know, I know where the screen is on the desktop. I use the X plus XY and then times the screen scaling, because you can have different screen scalings. So and then I've turned the value from the game board value into absolute value on your desktop screen. So then I know where to move the mouse for that one. Cool. And this looks a lot, but don't worry, this is actually pretty simple. So I call that function to know where I need to be absolutely. I move the mouse there. So this is just a Windows mouse input, where we are, X and Y, absolute movement. Let's move the mouse there. I click down the button. I get the absolute position for the end position on the screen. I move the mouse there, and I release. Click, then move, click, drag, release. Cool. So, who wants a live demo? Visual Studio. Update ready now. Let's launch this one. That should be the bejeweled one. I think that should be the right location. So who again prayed to the demo gods, right? Good. Let's click play. Yes. It found the special move. So here's the thing. You see this is playing pretty fast, right? There's a 200 millisecond sleep function on this, because it's too fast. I learned that you can match stuff in the air. When stuff is falling, it will find a match, like, oh, here's this white one that's below these other ones. If I move that one, and in some cases, the game is like, sure. Let me finish the level. Yay. There we go. Cool, right? Demo. So we prayed correctly to the demo gods. Good, on my own time. All right, I'm all right. Okay, I can be less stressed for the next session. Cool. So we have that. Let's graduate, right? Level 3. What if the game has none of this, right? Because yeah, you can imagine a lot of applications you want to interact with, they're not so nice. They're not everything is a cool little grid, right? So there should be even fewer. So who knows this game? Okay, more than I thought. For those who haven't, this is a great game. This is called VVVVV. As again, a great name. Very Googleable. Kind of looks like this. This was the nice little GIF I found. So you are a character, move around this world. You have these screens. The spikes are bad, and you can't jump. But since you're in space, you can reverse gravity. So if you hit spacebar, you'll flip the gravity. So you want to do these moves where you like try to avoid spikes and do these things by reverting gravity. The game isn't actually this complex, but this was just a little fun GIF I found of the character moving around. So the game does not have built-in support for just giving the game the inputs like Doom has. I can't just give it the inputs. It does not have a simple game state. There's not a cute little game board. It's a lot of levels. Things go all over the place. And it's actually fast-paced. Like this is very, like you need to be pretty accurate with what you're doing. You can't just randomly just click the mouse and just hope things match, because then your character might die, and then, because in Bejeweled, I could make a mistake. It doesn't matter. But here, if I make a mistake, I run into the spike or whatever, and then game over. So I need to be pretty accurate. So this is what I initially thought. I was going to become Hacker Man, right? Again, a great little short film. But I wanted to be Hacker Man, right? But what I turned out to be is this guy. Because the stuff you have to do to get to this stage is more this and less this, right? But it's fun. So before I continue on with that madness, there's one thing I need to talk about, which for people who don't play games might not know. The game loop. So games are applications like any other, but games usually follow certain steps. We get the input from the user. We update the state, whatever that state of the world of the game is. And then we take that current state and we draw it to the screen. And then we go back, get the input from the user, update the state, then draw whatever's on the screen. There should be like 50 asterisks here, but if you want a mental model, this is fine. Again, yeah. What if there's no input? Or we're not great at handling input where it might be delayed or you might miss input. It depends on how you implement it. Updating the game state can take very long time. And that even can be multi-threaded. That can happen in a different thread and then or many threads, and then we just pull from that state. Or the drawing itself might be multi-threaded, but then there's a join point where they copy the state over and then they do the drawing. So you have that separate. So games are in all of these flavors, right? So again, a little flowchart model. You initialize the game, then you start processing the input. You update the game state, you draw, you go back up. This might seem like repeating, but I need this picture in a little bit. So this is called a frame, usually called a frame. Processing inputs, we don't think about the time that takes. Less than 1 millisecond, less than a microsecond, it doesn't take time. How this long takes, depends. That very much depends. Same thing here, it depends. But if you want the game to run at 60 FPS, this whole thing cannot take more than 16.66 milliseconds. That's the time you have. So if you want to do any work that will take longer, you have to defer it, or you have to do it in segments, right? Another way of thinking about it is this needs to also update at least 16 milliseconds, because if the drawing is just happening, like that's just pushed out of the way and something else does the drawing. Because that can also happen where you're drawing just old state, or you're drawing, what can happen is you draw half a state. It's called tearing. Like you have half the state because the screen's refresh rate, like if you have if you don't have VSync on, you can actually get half the state drawn to the screen. So, and we draw this as often as we can. So if we get some code examples, yes, I'm good. Get some timer stuff. What's the current time? We have an infinite loop. I love those. So what's the time now? And what's the difference between what we had and what we have now? Which is, of course, in the first frame, nothing, but let's imagine we've been going for a while. And then we have an accumulator. So we're slowly adding to that number. How long has it been since we've been doing work? I can process the input, some function, whatever that is. And then I say, if the accumulator, whatever time we've been accumulating, is more than the delta time, and the delta time is the 16 millisecond thing, which means that we owe a state update. We are in debt. So I update the game state and I reduce the accumulator. This also means that if whatever we have accumulated is less than the delta, we don't go in the loop. We don't update the game state, which means that the game state updates at a regular tick, but we might draw more often. So then we draw. So that loop, what it does is actually two things. We might owe state updates. So if the accumulator is like 100, we have to update the state a few times before we're debt-free. Or the accumulator might be less than the delta time, which means that we don't do anything. But in most cases, we owe one update. Then we owe one update. You can, if you make this kind of application and you have an application window, you can test this by clicking on the header bar and dragging it about and releasing, because that freezes the loop. So then you owe time. Okay, so this is another way of thinking about this kind of stuff. There are as many variations of this and blog posts about people arguing what is the best and whatever, but nice visual model. So yeah, arrows pointing to the thing I just said. Great. So the reason why I picked this project, there's a few advantages this project has. It's open source. Because like, okay, I want to do this exercise on an application I don't have control over, but if there's a problem, I would like to go and check. That would be nice, just so I can show you and if I don't have any problems. So here's the actual loop. Ignore the const volatile. Welcome to game dev, but things can be weird sometimes. There's an important thing in this loop, which I then found, is because we learned here that update count might happen more often. So what I want from a game is that we do one process input, we do one game state update, and we do one draw no matter what, because that makes our job easier, right? If you have the other way around, you're doing the same thing, but your job is just harder. So it's single-threaded as well, and the game actually has options where you can go and set the game to that value, because normally the game wants to run as fast as you can, but you can go in and toggle these settings, so then the game will do one update, one input, one update, one draw, always, which makes our life very easy. Cool. So here's my plan. Launch the game as a paused child process in some loader. So loader, game process, my DLL. Hook the function that creates a DirectX device. Get the address of that device. Intercept the game's draw call and call our function first. And then before each frame, we send our keyboard inputs. Sounds like a plan? Hacker man. So here's the image again. So here, the game is doing this one at a time. Here's where we intercept. We call whatever the game wants to happen. Fine, let you draw. But then we send those inputs to Windows. We tell Windows, hey, someone pressed a key. Someone did something on the keyboard. We can actually do this here. We can hook the input polling functions. But the advantage of doing it in the draw state is you can then also draw some debug UI. So that's kind of an advantage of like, because if you do it in the process input, you kind of can't do much else. Okay? Good. So you might also think, wait, that's illegal. And Windows thinks that because when I do this, operation did not complete successfully because the file contains a virus or potentially unwanted software. But no, I want this software. Even here. Contains a virus or potentially unwanted software. Here's the issue. I can't run this in release mode. I can only run this in debug mode. So if you have a solution to that, you can talk to me. So I use a thing from Microsoft called Detours. What Detours does is helps you create these intercepts. There's a function somewhere, I want to replace it with my function. You can use Detours, it's very lovely. It can get a little hairy in how you do this. If you've never done this kind of stuff before, you usually want a pointer to their function, wherever that function lives, and you get a pointer to it. You create your own function. You can do stuff before or after, but at some point you need to call their function and then return the value. And then you have your function, and that's the function that is replaced. So what Detours will do is it will call your function, and then you will call their function. That's kind of what happens here. Okay? And those who haven't done DLL stuff, this is usually what DLL main looks like. And especially for Detours, you init Detours, you have a process attach or process detach. So when the process comes alive or not, you do some init, you create a Detours transaction, and then you hook your function. You need to have a transaction, you need to update the thread to say like, hey, we're going to do something. You need to attach the function, and then on the other side, you do the reverse, you can unhook. We actually don't do that. We're actually I don't do that. But it doesn't matter much, but you can detach things as well. Because then, once this happens, anytime the application wants to call their function, they're actually calling your function. And there's a library called Frida that is very good at this. If you want an actual library that does this for you, the library called Frida. Frida.re, I think. Very good. So, and the game, the VVV game, runs DirectX 9, which is pretty old, but it's fine. I thought like maybe there's some example code of how to do hooking with DirectX 9, and I found this. It was perfect. So thank you, Tom Gascoigne, and if you're watching, your code is great. So this was like a test example. I love the commit. Whoops, forgot to commit the new class. Just the latest commit from 12 years ago. But hey, it happens to all of us. So this founded the basis. My code doesn't look like that, but this got me going. So this was really good. So this is kind of my main. So I have two things. I have a loader, and I have the DLL that I'm adding into the game process. So my loader looks like this. I have the name of my DLL. I want to create the process suspended, and I call detours by saying create process and then suspend it. So I want to spawn the game. I want to create the game, but I want to spawn the game with my DLL in it. And it's suspended. So the game actually doesn't do anything right now. It's just sitting there waiting for someone to kickstart the game. Then I can start the process, and then I wait for it forever, and then my process quits. So I spawn the process, and then I sit and wait until the process is done, and then I quit when that's done. So I follow the game, okay? But once my DLL has been hooked into the game, and the game is still suspended, I actually get called, and I can run. Even though the process is suspended, I can run. So my DLL main, I can call hook create device. And then I can call my little function and do my little wizardry. So, and I don't do anything in the other ones because it doesn't matter too much. And, oh yeah, and if you're doing this kind of stuff, message box is your best debugging pal because you kind of can't debug otherwise. It's kind of tricky. And I can throw a message box and I can get a hello hook, right? So this worked, great. What's the next step? Well, the game is going to create the drawing device at some point once it unpauses. So what I do is I create one. I'm going to create one. And I'm going to, so avert your eyes. I'm going to extract the vtable. And it's a double dword cast, which is a great one. So now I have a pointer to the vtable for that object. And then I should release it. I don't care about it. I just need to know where it was, right? So now I have the vtable. Cool. So I have made a little structure that I can unprotect that memory. So I can say, this is the pointer to in the vtable that I want to unprotect. That create device, I saved where it was, the function itself. It's usually at the same place. So create device is at offset 16, and the end scene, which is the draw one, is at offset 42. So what's the size of the thing I want to unprotect? It's dword. What I want to do with it, I want to make it readable. And this is the function I want to run on that. So I want to take the original create device and save it somewhere. I have a function pointed to it that's from the original. And I want to replace it with my function, right? So when the game at some point unfreezes and calls create device, it calls my create device. Yay. So summary, spawn the game process paused. Attach our DLL to the game process. Hook the create device function. So when the game starts, we get that. And then now we need to just, once the game does that and creates the end device function, create device function, we need to hook the end scene function. So when the game wants to draw its thing on the screen, they're actually calling our function. Okay? So this is going to be a little messy, but it's going to be fun. This is the create device function, and it has some arguments. I don't care about these arguments. I just know they're there because what I'm going to do is I'm going to be a good person and create that device for the game. So I'm just taking these arguments and sending them in. I don't care what they do. They probably do something really cool and fun. So now I've been a good person and created the device for the game. But this then also means I have the device. Little message box for good safekeeping. I protect to reset the pointer that I did initially for the create device, just to, again, be a good person. And then I take that returned device, that is now our new vtable, and I find the original end scene function, and I replace it with my end scene function. So it's the same idea, just with another function. So now when the game wants to draw something to the screen, they call my function, not their function. So how does that? So yeah, if I do a message box on the function, I get the game screen up and running, and I get an alert on that one. Yay! Where are we? Okay, we're good. We're getting close to the end. So here's the function. All right, seems not that great so far. I call the original end scene because I want the game to draw something to the screen. I count the frames. And what I can do is, on frame 1, I want to send spacebar input. On frame 2, I want to send release spacebar input. This works. This works perfectly. And because the game is always doing things at the same time, this works, yeah. So what I can do is, I can create a little more complicated function that loads from a file some commands, saves them into a vector of commands, and does that only for the first init. And then I have a very complicated file format. So big S is pressing a spacebar, small s releasing spacebar. Big D is pressing the D button on the keyboard, little d is releasing the D button on the keyboard. So this means on frame 2 of the game, I'm pressing spacebar. On frame 3, I'm releasing spacebar. So I can play the game exactly one frame at a time. Haha, the title of the talk. And the dash is just nothing, so I can have like a wait timer for that. And then this is the implementation. Read, like if you're on frame X, and that frame data said S, then call press space, which is like one of the functions from before, just the Windows send input of pressing the spacebar. That's the whole thing, right? So, what's a demo, right? Demo gods, take 2. I am here, so I want to say load there simple. Maybe not have the presentation in full screen here. Yep. So load that, press enter, and the game. Now it's playing. And then at some point, press the space, I go into this hole. I avoid the spikes, boop, boop. And there you go. Plays the game. So if I run this again, like we talked about, I wanted to have some debugging tools. Because I have the render function. So I can put a sleep in the render function. And in the corner, it says frame 52, 53, 54, and you see the millisecond delay of each. So this is how I built the file, is that I know that if I wanted to press space, let's say let the character go, I wanted to press space here, it's frame 65. So I'd go to this frame 65 in the file, line 65, handy, and put an S there. Very high technology stuff. And then I would just play it again and try it out and try it out. I can even pause it, make it go a little bit faster. So if I want to fast forward a little bit, just normal. And then I can actually, I have the buttons here as well if I just want to test it out. But you saw, I froze it and it's still playing the same way. It's like playing the demo file, right? So I have a little bit more tricky example, and I'm going to slow it down immediately. So this is a puzzle section, very hard. And I want you to see a land, spacebar, there. So there's a thing in games called coyote time, where once you go off a ledge, they actually let you press the spacebar to flip around for like a frame or two. Because otherwise it feels weird or bad. Let's go forwards a little bit faster. Here. So we're going to land here. And I want to press spacebar. Good, I press spacebar. Very exciting, like, whoa, what's going to happen? But it's always going to do the same thing. Very close, right? No, press spacebar here. The next one is the best one, right? Go here, down, down, still able. Because the game is like, no, it feels nice if you're allowed to press the spacebar a little bit later. Then I get the checkpoint, and I can play the game. So that works nicely. I can do normal, and then we go and collect our little trinket. Yay, that works. So for those who played the game, so for those who haven't played the game, this will look weird. For those who have played the game, this will look very funny. So there's like an extreme challenge in the game where you have to like avoid the spikes all the way up, do like a small maneuver at the top, and go all the way down and avoid all the spikes. And then, yeah. So for those who have played the game, this is interesting, but this challenge is this took me like an hour or something doing myself. Because there's so many, if I slow this down a little bit, spike, See, the spikes aren't perfect, so you can kind of play with them. We have to go in there, which is a way people never do. And we don't have a lot of time. We have like 3 frames to press that spacebar button at the top. And then you have to go all the way down. I think I come close to one spike as well. There, yeah. There you go. And I made a couple of demos where I landed on the little pedestal there, or I landed back on the other side, which is kind of negating the challenge, but it's kind of funny. So yeah. Oh, and another thing, like for those who are curious, I'm playing this game every time, and the trinket is always there, but the trinket is saved when you get it. I'm overwriting the save files, for those who are curious. I have all the save files, so that's why I can do this again and again. So I have all the save files, I can just overwrite them. This is how I can do the demos again and again. Just a thing I haven't shown in the demo. Okay, where are we? 4 minutes, perfect. So, summary. Games are neat, and it's fun to play with them programmatically. When you have an application where you don't have the source code, there are still ways to automatically interact with it, right? AKA, and this is gonna be, yes, you can still test that old legacy application. And you can still do kind of safe refactoring to it, as we've seen. So yes, this was a talk about testing. Write more tests, right? So we had all fun in games, but yes, you can. So if someone has an excuse of like, no, we can't test that old legacy app. Like, we have the approval tests, or it's hard to interact with the application testing. Like, you can write stuff that detects a button or looks for a thing on the screen, and you can totally do Windows interactions with it. Or even better, program your application so you can do programmatic interactions to it, because it makes testing way easier. That's what the web does a lot. They do like interactions with Chrome and that kind of stuff. So write more tests. If you're curious, this is more for curious people. If you're interested in kind of this automation of games, tool-assisted speedruns, it's called. There's a website for that. They have emulators for a bunch of games. So if you look at that, you can play and see what people are doing. The stuff I saw with the spikes, that's baby games. Like, people are doing wild stuff to games, absolutely. If you're interested in Doom, that we had before, Doom Speed Demos Archives, I had a lot of help from them. The edge cases I'm using to test are actually from the Doom community. They have a lot of like weird interactions, so I can put them in the demos and then use that as the CI/CD test for the GitHub thing. So they have a lot of like weird engine quirks, so you can maintain the weird engine quirks. Code, if you want to look at, it's everything is on mine except the last one is Patricia. That's for CPP Doom. The first two, I mean, these are weird like projects to prove a point, but yeah, if you want to look at them, you can. And that's my face again. So yeah, thank you. $300 exactly. Shush. Questions? Thoughts? Comments? Angry rants? A perfect talk? Okay, thank you.